Okay. Go ahead. Thank you for the introduction. So my name is Aleksander Borg-Gruszecki, and as introduced, today I'll be talking about the effects capabilities and boxes paper, which is joint work of Jonathan Brachthäuser, Philipp Schuster, Ed Lee, and me in this order. And what I want to say right at the beginning is that we have an online demo, an artifact that was recognized at OOPSLA, and we spent a lot of time on it. What it is, it's an online playground with all the examples from our paper where you can type check them and run them and edit them as you wish. So if you would like to know more about our work, that should be the first place you go to right after this talk, and there will be even a huge QR code at the end. And this work is done in the context of the effect language spelled with a K and developed at University of Tübingen at Jonathan Brachthäuser's research group. It's a new language with effects and handlers. And in this particular talk, we will be talking about how it explores lightweight alternatives to traditional effect systems. So our roadmap is that first we will talk a bit about traditional effect systems and the alternative path that effect takes, which is capability-based effect systems. Then we will talk about how to establish effect safety with capabilities. And finally, we will see how to mediate between the two systems with boxes, which is the major contribution of, which is the real topic of our paper. So we start with a puzzle, a snippet in a language with effects and effect handlers. And the question is, where will the throw operation be handled here? And in case that you are unfamiliar with exceptions, please imagine that this is a JavaScript snippet, and instead of, and we just have a throw here, and we have a catch here, right? So where would this throw be handled? Do we have a guess?
Is this a func being passed a higher order function?
Yes.
So there's a parent missing, or it doesn't?
Yeah, I mean, yeah, we pass a func, and we do not know where the throw will be handled, right? Because, I mean, we probably intended it to be handled in the with clause, but the higher order function, it can interfere with that. It can observe the exception. And effect handlers, they work similarly to exceptions. At runtime, there is a dynamic stack of effect handlers, right? And when we perform an effect operation, we essentially address the first handler of the top of the stack that can handle a row exception. And so, depending on the language and depending on the signature of higher order function, it might be possible that it can observe the throw operation that we are performing here. And so our first conclusion here is that the traditional effect systems and effect handlers, they are dynamically scoped. And the second, a bit subtler conclusion is that in these systems, it is a bit difficult to address a concrete effect handler for our operation. Since remember, the addressing is done relative to the top of the stack. And so the alternative in this in system C from our paper is that we explicitly name the handler, right, as EXC here in the with clause, and we reference that handler when we perform the throw operation, right? This is also done in other work. And so what this does is that it syntactically establishes that it is our handler that will handle this operation, right? So in our work, we would call EXC a capability, right, to throw effects. And we see, to throw exceptions. And what we see here is that these capabilities, they establish lexical scoping. Okay, and now I would like to talk a bit about signatures. So we are back to a language without capabilities, with traditional effect system, and here we have a utility function rethrow. The idea here is that we take a prog closure, we run it, we catch any exceptions that prog might throw, we add a description to them, and we rethrow them outside, right? So nothing too complicated, really. And the surprise here is the effect signature that will be assigned to this definition by some effectful languages. For instance, Coca will correctly infer this most general type. And as we might see, it might be a bit surprising. right? I mean, what's surprising is that, for instance, here in the signature of the scribe, we have EXC, but actually there is no exception that is, there is no try lexically enclosing the scribe. And likewise, in the type of prog, we actually have two occurrences of EXC. And this might be, I think it's fair to say that this might be surprising to a beginner. And there are good reasons why Coca infers the signature. They have to do with effect parametricity and with using unification for effect inference. But still, we are exploring a different path in our system. And so if we were using capabilities in system C, this is how we would write refrow. So you see that now we explicitly take a capability as an argument. We explicitly name the capability that we define, and we pass the capabilities to the points that they are supposed to be, at the points where they are supposed to be used. And the signature of refrow in our system would be the following, terser one. And the goal of our work really is to explore how we can assign, how we can have an effect system with ergonomic signatures such as this one that yet remain as expressive and as precise as the signature that we have seen previously. Right? So let's now see a side-by-side comparison of traditional and effect-based capability systems. So in traditional ones, effects are an additional output. We see that in the typing judgment, if we are typing a statement S, we assign it an effect set EXC in this case, right? And what this tells us is that S, when it is evaluated, will at most throw exceptions. And likewise, we also have an effect annotation on the function arrow. And so these effect sets conservatively approximate what effects will occur during evaluation of statements. Like we have seen in our examples, they are also connected with dynamic scoping of effect handlers. And finally, they encourage type-based reasoning, which is to say that just looking at the type, we can reason about the possible effects of statements. In particular, we can say that something is pure. And so what do we do in capability-based effect systems? They still enable a form of reasoning about effects, right? I mean, we know that capabilities are effects for free. And so the reasoning is just slightly different. So the capabilities, they express a requirement on the context. If we are typing a statement S, then it can use a capability EXC merely because it is in the context which we are using to type the statement. And likewise, a function can express that its calling context should provide it with a capability to throw exceptions by taking this capability as a parameter. So capability-based systems, they approximate which effects can be observed, right, by the calling context. And by observed here, I don't mean observed by some side channels, I mean observed by being handled. If I call a function of the type that we see on the right, that means that I can observe the effect EXC, but not effects which are connected with any capabilities captured by this function. And so, like we've seen in these systems, both effect usage and handling is lexically scoped, and they are connected with what we call scoped-based reasoning. Here we have an illustration of what we mean by that. We have some function myModule, which takes two arguments, console and time. Now, if this was a snippet in, say, JavaScript or Python, right, then I would be able to use these capabilities, really, merely because I have taken them as arguments, right? And so capability-based systems, they preserve this form of reasoning. In the local definition, say time, I can use console and time merely because they are in the current scope. And this is also reflected in the types that we assign, because the type of say time does not mention that it may perform some effects. And this is because it is not necessary to do so, because we already know that both console and time are available in the current scope. Okay, so now the question is, now that we have these more ergonomic and terser types, does that have some effect? Does that have some effect on effect safety? Well, the most important thing to talk about here is the idea of closing over capabilities. In capability-based effect systems, lexical closure is the main mechanism to obtain effect polymorphism. If I define a higher order function, then the argument to this function, like this closure over here, can close over capabilities from the calling context, just by closing over them, right? And so this means that higher order functions in such systems are naturally effect polymorphic. And that's also a bit of a problem, because if we take the same closure and return it from the try block, we actually have a problem. We break effect safety because we return exc from the scope that binds it. So if I try to run this closure, underlined, after the try block is left, what will happen is that I will try to locate exc on the handler stack, and I will get a crash because it's no longer there. So crashes are bad. We don't want crashes. This is why we have type systems. So what do we do with that? Well, one idea is second-class values presented at OOPSLA back in 2016. And in this discipline, we distinguish between first and second-class values. Second-class values cannot be returned from any scope, cannot be stored anywhere whatsoever, and cannot be closed over by first-class values. And first-class values are otherwise unrestricted. So really, the important idea here is that second-class values only ever travel up the call stack, if we imagine the call stack to grow up, right? They cannot ever be returned from the call stack. So that means that, as was observed in this paper, if a function cannot leave the dynamic scope it is defined in, we do not need to track its effects to establish effect safety, right? And second-class values observe this restriction. And so effect embraces this idea. In the upper right corner here, we see a function signature in effect, and we see that it has two sorts of parameters. We have, in parentheses, first-class value parameters, which is for data such as integers or booleans or user-defined ADTs. And in braces, we have second-class block parameters, and that's for closures and otherwise functions and capabilities. And we say blocks here just to distinguish from first-class functions. Okay, and so if we have this discipline, right, then that means that we can have some higher order functions without violating effect safety, right? I mean, for additional context, remember that we can't smuggle a block in a first-class argument because they cannot close over blocks. Okay, and so the slogan of effect, so far at least, was that there simply are no first-class functions. And that reportedly, as Jonathan tells me, made some people anxious, but again, that's all right, because we still can have useful higher order functions. We just can't have first-class functions. However, it did work. It did work to an extent, right? But to an extent. And so what this paper is about is to amend this, but without losing track of the ergonomic type signatures that we were after from the beginning, right? And so the remainder of this talk will be about that. Will be about bringing back first-class signatures while preserving the ergonomic types that still allow us to reason about effects of functions. And we will be taking two steps towards this goal. First, we will be tracking more details about what makes a value second-class, the degree of second-classness, say, and then we will use this information to bridge between second and first-class value with boxes. Okay, so first, generalizing second-class values. Here is an illustration of the sort of information that we track. We have three definitions. First, say time from before. Then we have repeat, which repeats n times a block f. And finally, say time price, which mentions both repeat and say time. Now, if you were to take these definitions and put them into our online playground, what you would see is much the same thing as what would you see in an IDE of effect. We would have these effects pop up. These sets pop up over the definitions that we wrote. So over, say, time, we would have the set containing console and time. So the capabilities from the defining context of, say, time, which were mentioned in its body, right? Over repeat, we would see an empty set. We don't have f there because it's just a parameter to repeat. And finally, over say time price, we would see console and time, since say time price mentions say time. But that's a local definition and not the capability itself. Okay, so how do we deal with this formally? Well, we start from the syntax of types. There are three syntactic categories responsible for that in System C. We have value types tau, again, ints and booleans, boring constants. We have block types, which are multi-argument functions, and multi-argument, since carrying, as Jonathan likes to say, is the root of all evil in effect systems. And we also have, here in this category, we would also have capabilities. And finally, we also have capability sets, which are exactly that. And then all the magic is in the typing contexts. We have value bindings, they are boring. We have tracked bindings for capabilities, and we have transparent bindings for capabilities. So what's that about? If we had console or time, those would be bound with tracked bindings because they are basic capabilities, right? They don't close over anything. And then say time is a local definition that might transitively close over some capabilities, and so it is a transparent binding. And notice that the annotation here is on the binder, like in, say, a coeffect. We preserve the types that, the ergonomic types that we are after. Okay, so now for the syntax of terms, pure expressions, boring. Blocks, there we have multi-argument abstraction literals, and then effectful statements. So from the top, we have local bindings for blocks, block application, since remember, blocks are the functions, right? We can't apply an expression, we apply a block. And we have val and return, which are similar to, which are the monadic operations. Val sequences two statements, and return injects a pure expression into an effectful statement. Okay? So now the typing. Expression typing, boring. Block typing. In the upper right corner, you see that we have an additional output, which we call context restriction, right? So that output is a set of capabilities which are necessary in order to evaluate this block. And it is always, we call it a context restriction, since it is always a subset of the bindings in gamma. So where do these things come from? For transparent bindings like say time, what is put in the restriction are the capabilities transitively closed over by these bindings. And for tracked capabilities, what we get in the restriction is the capability itself. And these are the primary ways in which things are added to context restriction. And then we also have subsumption, but it is restricted to context restriction. We do not have subtyping. Okay. Then statement typing. It also has a context restriction as an output. When we are typing return, we always have an empty restriction, since remember, return injects a pure expression. Val merely sequences statements, so we just collect the restrictions and take a union of them. What def will do is that first it will type the locally bound block B, it will obtain a restriction, and it will move it to the binding that is there when typing the statement, right? Then we'll also have subsumption, and to illustrate how the typing rule for def works is that when we would be typing say time, we type the body, we see that it requires console and time, and so that is what gets put in this bluish capability set. That is an annotation on the binding of say time. Okay, we are very good on time. So finally, we move to explicit boxing, the way we mediate between effects and capabilities. And really the key insight of our paper is that we can preserve the ergonomic signatures that we are after, and we can also have precise types that do not require second-class functions if we reflect capture of functions only as long as the function is used as first class. So let's illustrate that. Here we have the repeat from before, and here we have an alternate version of it, which is carried. First takes the block F, and then takes the number of times it should be repeated, right? So now we are trying to return something that captures a block, right? It was disallowed so far. And what we do in this work is we add an explicit box term inspired by box modality and various lines of work on that. And on the term level, this needs to be done explicitly. And what it does is that it will give us a first-class function whose type reflects the capture of this function, right? Here we capture f, and so we get that f in the function type. Okay? And so to illustrate more how this works, we have a reminder of the types of repeater and say time here. And now, in fun1, if we try to box a block that mentions console, then that's what we will get in the type. If we have, if in fun2, we box over a local binding, then what we have in the type is the capabilities transitively captured by the binding. And finally, in fun3, if we apply repeater to say time, what we will get in the type of the function returned by repeater is console and time. So notice that we also have a form of polymorphism here. Okay, and now for unboxing. So fun1, it cannot be applied by itself. It is actually an expression. In order to apply it, we first need to unbox it, which is done, again, with an explicit unbox term. And what that does is it converts an expression to a callable block, right? And so it will take the information from the type of fun1, and it will put it back into information tracked on the bindings, right? And remember that we can't ever unbox something that that has a capability which is currently out of scope, because we can't even type that, that sort of boxed capability. Okay, so how does this look formally? We have a box term in expressions. We have a boxed type in the syntax of value types. We have an explicit unbox term, and we have these typing rules for box and unbox, which are suspiciously similar, which are suspiciously simple, right? So box merely takes the restriction from, which is outputted by the typing of the block, and moves it to the type, and unbox just does the opposite, takes the capability set from the type and moves it back into a restriction. And what's also important to mention here is that formally these terms are explicit, But if you try to experiment with our online playground, what you will see is that we can actually infer them. And so they do not need to be explicitly mentioned by the user, explicitly written by the user. Okay, so to summarize, what we have seen about our system is that we track references to capabilities on binders, and that we wanted to preserve the ergonomic type of refrow from the beginning and ergonomic types of various functions in general. And we can do that. We can do that if we only reflect capabilities in types of first-class functions. And in our paper, we also have a full formalization and a soundness proof mechanized in Coq. Thank you, and I'm happy to take your questions.
Thank you, Alexander. So are there questions? I see one down here. No, down 2 rows down.
Sorry. Yes, when you showed the example with the exception and trying to throw the exception and then hopefully needing to make sure that the exception handler is still on the stack, right?
That one.
Yeah. That seems like something that you might be able to solve with something like Rust borrow checker.
I mean, in principle, yes, but borrow checker is a system intended to solve like a different problem. I mean, here we are really starting from a system that has these second-class values, right? And we are trying to add the minimum, which will let us still have first-class functions, right?
But like Rust already has first-class functions, so like how would it compare to just basically track this as a lifetime? The functions themselves.
Okay, how would it compare to tracking? Well, I mean, the general point here is that typically we don't really need to mention like anything in most types at all, right? It's that we only need to start mentioning things in very particular cases, and this is what the boxes let us do.
Yeah, I see what you're saying. It's much less verbose.
Mm-hmm.
Thank you for an interesting talk. I'm curious what the difference in expressive power between this system is and a classical effect type system. Do you
That's
have an
a very
answer?
good question. I mean, so the interesting thing is that, I mean, in principle, there actually isn't. Okay, so technically speaking, we don't actually have capabilities at polymorphism, right? Parametric polymorphism. We don't have that, and that's the primary distinction. But otherwise, the types, right? I mean, if we want to have first-class functions, they track exactly the sort of information that we want to track.
Yeah.
Right. So when it comes to expressiveness, right, I don't think there is that much of a distinction. There are differences in. I mean, even if we want to track what effects might be performed by functions, right? We still can do that in this system, right? I mean, if we really want to see what capabilities are used by some closure, right? If we make it first class, we do see that, and so we can even track if something is pure. I'm not sure if you have a particular.
Yeah, I mean that's not that unsurprising because actually, even when you have effect polymorphism, you don't really need it. Or there's only one way that you can instantiate a function that gets passed as an argument. You have to instantiate it to have the current effects because you're using it. So, I mean, that's the game that Frank plays, for instance. So maybe that's not surprising, but you've not done a formal translation, though, from an effect-based system into yours?
No.
No, okay. That would be interesting to try. Anyway.
Yes, agreed.
Okay, thank you.
Thank you.